Another mechanism that we could use to reduce the size of this mapping table comes with a very simplistic idea that initially we are storing the mapping of one logical entity to a physical entity. What if we increase the size of this logical entity? So rather than storing a page for a page where we have to maintain one entry for each page, what if we maintain one entry for groups of pages? We could call it a chunk. We could maintain a one entry for a block. Block is again group of pages, right? So this idea, like the mapping techniques based on if we are storing this groups of pages, if we are storing one pointer for one block, we can call it as block-based mapping. If we are storing one pointer for the chunk, we can define chunks as combination of multiple blocks or something. We can call that as chunk-based mapping. This technique of chunk-based mapping or group-based mapping is evolved with a simplistic idea of let's map logical chunks to physical chunks. And these physical chunks can also be aligned to the block boundaries. And in that case, it's called block-based mapping. So now instead of storing one entry for each page, we are just storing one entry for each block or one entry for each chunk. And definitely that will allow us to reduce the size of mapping table considerably. But nothing comes without the problem, right? So what are the problems of such chunk-based mapping? Would give you a minute to think about that. Clue, think in the basic operations that we need to do on SSD, read, write, and erase. Well, many of you have nailed down your problem. So if it aligns with what I'm saying, good job. Otherwise, better think next time, right? We have those think times in our lectures. So do your best to think it through next time we have any think time. So the problem is with, let's imagine if you have writes that are of the size of chunk or the block, then there is no issue. You just have a single pointer for that writes or single pointer for that updates, everything works magically fine. But if you have writes that are smaller than the size of your chunk or the size of your block, then, well, yes, that would give you a bunch of problems. So the problem is due to when writes are smaller than physical block or chunk size. And this would lead to significant write overhead. How it would lead to significant write overhead? Can you all think of that? Yes, because we can just maintain a single pointer for every chunk. So in that case, let's say if the block is the chunk, so if the granularity at which you are maintaining a single pointer is the block, And this block has many, many pages inside that. Not that I could draw all the pages, but just imagine many more. And the write just came for a single page inside this block that has many, many pages. Let's say 64 pages inside the block, and the write just came for one out of that 64 pages. What we would do is we would write that page, one out of 64, but then we are maintaining one pointer for that. So we cannot use the remaining 63 pages in this block anymore. Because if we store another data there, then logically the data, the first data and the second data, they would mean the same thing, which would be a blunder. So for every unique data in the operating system, we need a unique location to store that. And in this case, it's just a significant space wastage if we have write that is much more smaller than the chunk size. And if we reduce the chunk size, let's say if we reduce the chunk size to just a single page, well, then that's same as the direct mapping, right? We end up with that same problem of large, huge mapping table. So it's a sword with two sharp edges. Which way do you lean, and how do you balance this trade-off? From this balancing, from the idea of balancing the trade-off, you would be already thinking that why not try a hybrid mapping? And yes, you are correct. That is the way forward. So a hybrid mapping combines the advantages of direct mapping and chunk mapping. In a hybrid mapping, we would have in our SSD would have two types of blocks. A set of blocks that are indexed as we would do in a chunk mapping. So let's say if our chunk is a block, so we would have a set of blocks that have one entry pointing to each block. And then we have, let's call them as data blocks or data chunks. And we have another set of blocks in our SSD. Those have mapping to each page inside that block that have an entry, a pointer to point to each page, same as what we would do in direct mapping. And we can call this set of blocks as log blocks. So now, as you would already would be thinking, is that if we get and write to just a single page or just a very small entity compared to the whole chunk, very small proportion of whole chunk, we would direct that to this log block. And anyway, because we maintain a entry in our mapping table for each page in this log block, we wouldn't be wasting any space. And if we get a write that accumulates or that is of the size of the chunk, almost of the size of the chunk or the size of the block, we can direct that to the data block. So next, this is a matter to think. There could be a situation where we are out of number of log blocks. What do we do then? If you have so many data blocks still empty, but you are just out of number of log blocks, then there is a situation in which we would have to transition our log blocks into data blocks. And this transitioning will also help us to reduce the size of the mapping table, right? Some of you could argue that, oh, why do we need to transition? If we just have a block that's free in the data block, then just make it a log block. True, we could do that, but just imagine if we keep doing that, then we have the mapping table as same as the size of what we would have in the direct mapping. So that's not our goal behind designing this hybrid mapping. So we can do that, but we don't want to do that. Rather, what would be beneficial is once we have whole log blocks filled, we want to figure out a way to transition that log block into data block. And in order to do this merge of content from one or multiple log blocks into a data block so that the whole block could be represented with just a single pointer, there are multiple ways. We could either do switch merge, partial merge, or a full merge. Well, let's imagine that you have a log block with pages that are storing different information. Let's say initially you were storing in these pages, we were storing A, B, C, D, E, F, G. And we got an update, luckily, to all these pages. So all the pages got updated with A dash, B dash, C dash, D dash, E dash, F dash, and G dash. So how we could transition this update into a data block is initially if we had this block being pointed as a data block number 0, we would just erase all the content of this data block 0, and then we would have new content and then re-point this pointer of data block 0 to this new. This is just switching, basically switching the space between these two, switching the pointers of these two blocks. Switch merge, an easiest one, nothing to worry about, and very simplistic to do it without any overhead. But we might not be that lucky to have updates to all the pages in exactly the same order at the same time. So in that case, what happens? Let's say if our updates were only to happen to page A and page B inside this block, and remaining pages just remain the same. In that case, what we would have to do is partial merge. So we would have to initiate a data block in which we take this two data from the updated version, and then we take, now remember that this data is not stored in this place. It is stored in its original block over here. So then we take the data from the new one, we take this data from the old versions, the remaining data from the old versions, and then make it into a new block, and then we remark that block as block 0. So this is the process of partial merge, where we have to do some internal handling, some internal writing, so write amplification, but still we would be able to maintain just one entry in the mapping table for this whole block. And full merge is, now imagine the worst situation where just the order in which your updates arrived is if you have this multiple blocks, each having multiple pages, and we get the updates to these pages. Like, let's say we just got an update to one page from this at the first time. Then we got an update to the one page from this, one page from this. And then at a later instant, we got an update to the second page from this, first some other page from this, some another page from this, so on and so forth. And eventually, if we want to merge such log blocks into a data block, where we have a mix and match of valid and invalid pages within the blocks because of the updates that arrived over time, what we would have to do is fetch the valid pages from each block. So we know that, okay, in this block, the original version of this page is not valid because it was updated. Or the version of this page is not valid. This page is not valid. This is not valid. So these are not valid. But these content is stored in some another block at some another place, in some another pages, in some another block. It could happen that these all updated versions are stored all in a single block somewhere. So we have this over here, this over here, this over here, this over here, and same, we have these both as well stored in this new block. Now, while we are merging such, when we are doing a merge in such a situation of these log blocks into a data block, what we would have to do is fetch this page into the first page, then fetch this page into as the second page. And then we know the remaining 4 pages are still in the original version of the block. So fetch those. And finally, when we have that block ready, we can point that block and give it a single ID. Let's say block ID number 16. In the same way, we could reconstruct the content of the remaining 2 blocks by fetching the data from different blocks wherever the valid content exists, combining it all into the sequential order, and finally giving it a new block ID pointer. 17, 18, so on and so forth. So this is the process of full merge, which is way more overhead causing, and it would take much more time, as well as it leads to much more internal write amplification. But still, it would help us to minimize the size of the mapping table that we have to store. So now in this discussion of SSDs, we started by discussing the basics of how SSD cells are constituted, what are the challenges at the transistor level, how it stores the data, how we have different variants of SSDs, SLC, MLC, and TLC, depending on how many bits are stored in each transistor. Then we moved towards discussing how these transistors can come together, how can we accumulate flash to form a flash-based SSD, what components do we have on a flash-based SSD, including controller, including the on-chip memory, as well as the flash cells themselves. And then we looked into the hierarchy of how we can exploit the parallelism inside the flash, channel level parallelism, package level parallelism, plane level parallelism, so on and so forth. Then we looked into this, one of the major entity or major contributor of internal operations within SSD, which is flash transitional layer operations, which includes garbage collection, ware leveling, and obviously storing the mapping table. We looked into different variants of options that we have when it comes to how do we construct our mapping table, pros and cons of each. And we discussed the trade-offs between how we can construct a better version, which led us to this hybrid version of mapping table. So to conclude, definitely all these ideas would have given you some provoking thoughts to think of a better solution. And that's exactly what we need, right? Because SSD is still a technology that's being developed every day as we proceed. And it is not yet saturated by any means. So there is a lot of scope in designing new versions of it, developing new ways to solve the challenges that it provides, exploiting or taking advantage of the benefits that it gives in a different way. And hopefully the creative mind of yours is able to come up with some good idea, and that would be used even towards your project. Then to conclude, again, as we have the discussion topic needs to be revealed in the lecture, right? And I've not revealed our discussion topic yet. So that's something let's do now and conclude the lecture. The discussion topic of this module is for you to write your post on this 2 other functionalities or 2 other operations that happens within the SSD, and discuss your thoughts on how do you think these operations will be beneficial versus harmful by thinking in relation with SSD. What are these 2 operations? First, trim. Trim is an operation that is issued from the operating system, and somehow it may benefit SSD, it may be harmful to SSD, but that's your job to constitute or write your discussion post on. Second operation or second function that I want you to focus your discussion post on is over-provisioning. Over-provisioning is a concept that was introduced especially for SSDs that didn't exist for hard disk or was not that popular, was not that beneficial to have it for hard disk. So think of this operation, think it again in relation of the concepts that we discussed during this lecture, how over-provisioning could be beneficial, if there are any ways it could hurt SSD performance, reliability, or any of the matters that concerns to us. Think about all these aspects, and I'm looking forward to read your discussion posts. Thank you. Bye-bye.